Okay, so let's get started. We're happy today to have Justin to tell us something about Schrodinger CFTs.
Yes, thanks for having me. Apologies in advance to those in the audience who've seen this talk before. And yeah, so I would like to talk about this project I did with some students. It's very slow and dramatic, I suppose, where we were talking about we revisited the idea of Schrodinger CFTs, which was a very popular subject, I guess, in the early 2010s, late not. You think in your head about like three famous physicists, you think back to that time, one of them probably had a paper on some subject related to this, and then it sort of disappeared. So here's the archive number, and here's the three amazing students I did the work with. They did all the hard work, and then I get all the fun of traveling around and talking about it. And I guess every good talk starts with that philosophy, so I'll start with that. So quantum field theory for me is some general framework for describing physical systems at low energies or mesoscopic length scales relative to some microscopic scale. And there are many ingredients that can go into quantum field theory. So three popular ones are Lorentz invariance, unitarity, and locality as captured by cluster decomposition. And there's even a Fock theorem of Weinberg that says if you have all these three ingredients, then quantum field theory gives you some sort of unique description of physics in the infrared. If you have additionally scale invariance, this can lead to conformal enhancements, where you have, in fact, a conformal field theory. And conformal field theories are interesting places to do physics because there the kinematics is so strong that it's possible to bootstrap and understand the space of consistent quantum field theories. But I guess one point of today's talk is that none of these three ingredients are strictly necessary for doing quantum field theory. So you don't need to have locality. So for example, you can imagine you had a quantum field theory in ADS, and then you're studying sort of the boundary theory, or it doesn't even have to be an ADS, it could just be a quantum field theory with a boundary, and you think of the boundary as some quote unquote quantum field theory, but it's not local. Unitarity is not strictly necessary. You could have open quantum systems or something like that. And in today's talk, I'm actually going to drop Lorentz invariance. And this is perhaps even slightly natural from a condensed matter perspective. If you were a condensed matter person studying lattices, a priori, I don't see any reason why you would want to have Lorentz invariance. It often emerges, but it's not strictly necessary. So today I'm going to talk mostly about things that I call non-relativistic quantum field theories. So by definition, I'll say a non-relativistic quantum field theory is something with Galilean invariance. So just as a reminder, a little bit of kinematics. Galilean invariance has space and time translations. So here's how it acts as a finite translation. I put the infinitesimal generator here on the right. So we have translations in space, translations in time. Galilean boosts, this is some shift of the spatial coordinate proportional to how far you are in time. That's my generator Ki. There's also rotations. This is straightforward, acts by a rotation matrix on the vector, the spatial vector coordinates. And when you have this symmetry group here, this is called Galilean symmetry, and it also admits a central extension by a quantity here called the mass. So again, it's a central element, and I denote that M. You might complain, you already used M subscript ij. Why would you introduce another symbol called M? Mij won't play any role in the talk, so I've introduced a symbol called M. And yeah, so at criticality, much like the same way at criticality, or when you had scale invariance, you could have scale invariant systems in usual quantum field theory. At criticality, you can have scale invariance here in these non-relativistic scenarios. But a priori, again, there's no reason for space and time to scale now the same way. So generally, you'll have some sort of anisotropic scale symmetry. It's also called a Lifshitz scale symmetry. So in that case, D, when it acts on time and space, it can scale them differently. So here, if you can see in the back, T scales, or if X scales proportional to lambda, T scales proportional to lambda to the Z. Z is just some number. It's called dynamical critical exponent. And I just note for the record that if I had some mass, for example, if you ask how does mass scales with length scaling dimension Z minus 2. So you can actually already see that if you had dynamical critical exponent Z is equal to 2, then mass is sort of like preserved. It's like marginal for that notion of scale. So let me just recap. I know that was a lot of kinematics. Galilean symmetry is this. when you have scale invariant systems, there's this central element called mass. When you have scale invariant systems, you expect some notion of scale symmetry, but space and time don't have to scale the same. So you could have all different values of z. Z equals 1, z equals 2. You can even have negative values of z. It's a little weirder, but you can have it. And they describe real physical systems. So when z is equal to 2, specifically equal to 2, you can, as I previously mentioned, you can see that mass symmetry is preserved and is only at z is equal to 2. And in fact, there even exists then a conformal enhancement of that scale symmetry. This only happens actually for certain values of z, and at z equals 2 is one of the 2 special values of anisotropic scaling where you have this conformal enhancement. When you have this conformal enhancement, then you get some collection of generators. So it's everything I've already talked about. You have boosts, you have the mass symmetry, spatial translations, time translations, scale transformations, rotations, and this is the conformal, special conformal transformation. So that's the one extra generator you get. And altogether, these, if you have all of this symmetry, that's called Schrodinger symmetry. And today's talk is basically going to be about a little bit about general Lifshitz symmetric systems, but really I'm going to talk about Schrodinger symmetric systems. And this is, roughly speaking, the right notion of conformality in non-relativistic systems.
But you only have one special conformal transformation?
Yeah. Okay. You only have a special conformal transformation in the time fraction. That's right. Now, it's unfortunate for those at the back of the room, but I have some I have some commutation relations on this board here because I wanted to refer to them throughout the talk. And I'll just describe them to those at the back of the room. Okay? You'll just have to imagine the things I'm saying. It's these are the commutation relations. They're just some commutation relations. I guess I didn't also add in plus rotations. So everybody will notice who is on this angle of the room will notice, and you can tell your friends on this wedge of the room, that there are various spatial indices. So I didn't write out like the fact that PI is going to transform under rotation. That's really obvious. Let me highlight a few points of these. So does this red show up nice? It kind of shows up nice. So one thing to note is that under a dilatation, the space or the time-like translation scales proportional to itself, but it picks up a power of 2. Conversely, or on the other hand, if I do a space-like translation, it just picks up a power of 1.
Is it for every z or for z equals?
This is for z equals 2, exactly. So as Diego just spoiled for everyone, that is indeed a consequence of this z equals 2 scaling. And if I had z equals z scaling, then there would be a z here. Makes sense. And likewise, you can see the special conformal transformations scale the same way, but with a minus symbol. Everything else is basically some straightforward generalization of usual conformal symmetry. I also note with 100% foresight, because I've seen this talk before, that if you take a spatial translation and a boost, that they commute to this central element M. This is some fact which will be important later. Yes?
And so you have inversion in the time direction.
That's right, yeah. I mean, you can have inversion. Exactly, yeah. And
what's the other value of z where you get a more enhancement?
Yeah, so the other value of z is z equals 1.
Oh,
that's a good.
You said anisotropic.
Yeah, you're right. What I really meant was non-relativistic, not anisotropic. So z equals 1 is still non-relativistic. So it's you have the whole Galilean algebra. You also have a z equals 1 dilatation. Then you get conformal transformations both in space and in time.
Which are not the usual. It's not the full conformal group that I'm used to.
It's not. Yeah, it's not. That's right. Because that's right. It's not. So it's actually that's a good question. Maybe it's worthy of inversion. So if you have the usual conformal group, so let me write it. So.
But it's a contraction of the usual.
That's exactly right. It's the z equals 1, which is the contraction of the usual conformal group. You might think that makes it the more natural one. It's just not the one that shows up in physical systems as much. It sort of makes sense in hindsight. So it's even more confusing. So z equals 1 has the Galilean symmetry and the special conformal transformations in space. And it admits a central extension, which unfortunately is called M. GCA for Galilean conformal algebra. That's just the name of it. It's unfortunately called M. And the reason why I say it's unfortunate is because it has nothing to do with this M here. And that's also, roughly speaking, why it doesn't show up in physical systems. Because, you know, if you have Galilean symmetry and then some sort of conformal enhancement, this M here, if you don't break this M, you are never going to land on this thing here. This is the natural thing which shows up if you're going to preserve this central mass element. Does that roughly make sense? Good. And you know, funny enough, even though this thing here is the thing that you asked about is the thing that shows up as the Inuni-Wigner contraction of the usual conformal algebra. When you actually like take some physical system and you take like the non-relativistic limit with the fields or something like that, you end up with z equals 2. Okay, so that's a lot of kinematics. Yeah, so I'm going to study systems today here that have this so-called Schrodinger's. What happened? Like, there's a million white chalks, but I lost them. There it is. Okay, so I guess the first thing I should do is I should at least argue to you that such a thing exists, a quantum field theory with this Schrodinger symmetry, some version of a non-relativistic CFT. And here I go. I'm going to write down the Lagrangian for such a thing. So I dt plus lambda squared over 2m phi. So you can see why it's called Schrodinger symmetry, Schrodinger symmetry. This is sort of the analog of a free boson. This is kind of like our analog of the bosonic CFT. And so where do these sort of Schrodinger symmetric systems show up? Well, they show up in a number of places. One place that they show up is in a thing called the BEC-BCS crossover. So I know we have some condensed matter people in the room. So this same physical problem is also called trapped atoms. So atoms in a harmonic trap, or it's also equivalently called fermions at unitarity. I'll go into a little bit more detail about this in a bit. These Schrodinger symmetric systems also show up in nuclear physics. So nuclear physics ETs are sort of built from Schrodinger symmetric fixed points. So there's nice papers by Kaplan, Savage, Wise, and also Sridhar Pal on the EFTs for nucleon-nucleon interactions. One cute place that they've showed up very recently is, they've showed up more recently and also a long time ago, is in stochastic or Langevin systems. So these are stochastic / Langevin systems. So these are like sort of out of equilibrium physical systems or stochastic quantization. And in condensed matter physics, this is actually, the systems I'm describing are equivalent to what people call conformal quantum, let's see, I got this, critical points. There we go. Critical points, or CQCPs. And finally, a fourth place they show up is in null reductions and holography. So I'll show you a cute party trick if you're ever like, you know, at a party and you need to impress somebody. And what you could do, so how do they relate to null reductions and holography? So take your favorite CFT. Off the top of my head, my favorite CFT is the free scalar in d plus 2 dimensions. So take the free scalar. You know that the equation of motion is d squared phi equals 0. I'm going to write this in light cone coordinates. So my light cone coordinates are d plus, d minus, let's say minus plus, lambda squared of phi equals 0. And maybe I'll even write in the coordinates here, x plus, x minus, vector x equals 0. And then what I can do is I can do a Fourier transform in x plus, okay? And with 100% foresight, I will call the Fourier dual coordinate to x plus, I'll call it m. If I do that, you can just stare straight at the equation. You can see what does the Klein-Gordon equation Fourier transform to if I do this like Fourier transform. It Fourier transforms to I d minus psi m x minus x plus equals minus 1 over 2m lambda squared psi m x minus vec x. Oh, this should be vec x. So you can see that if I take the Klein-Gordon equation, for example, in d plus 2 dimensions, and I do a Fourier transform in x plus, or I do some sort of null reduction, I end up with a family of free Schrodinger equations.
But isn't it always the case Isn't it like the non-relativistic limit of the Klein-Gordon equation?
This part here is not the non-relativistic limit. No.
I mean, I could just take. I mean, it's kind of how you get there. You take a Fourier transform with respect to t, and you put the mass specifically, and you get something like that. What is specific here?
That's not what I'm doing here. So I agree that if I would have taken a massive field, a massive scalar field, and I would have rescaled it by like e to the, pulled out these plane wave factors, and then taken the low, like the speed of light to infinity, then I would have recovered a Schrodinger equation. I agree with that. That's not what I'm saying here. What I'm saying here is I'm taking a massless scalar field in one higher dimension, and I'm null reducing it. Yeah. What you're saying is also a valid way to get a Schrodinger symmetric system.
Point 3, what are you doing? You're doing some diffusion equation, adding noise, and then sometimes it goes to critical point. And that still has z equals 2? Always?
Yeah. Well, if the potential you add is dissipative, then you'll get z equals 2. Yeah. If it's that's right. For a general force. So hopefully that was some motivation. These systems exist. They are the non-relativistic analog of conformal field theory. They show up in a number of very physical situations. I guess so. The outline for the rest of the talk is pretty straightforward. I'm going to talk a little bit more about this canonical example, this famous example called fermions at unitarity. I'll basically talk about a whole bunch of stories that occurred in the literature. There was a whole bunch of very famous papers, especially by Nishida and Son, where they were using this techniques of Schrodinger symmetric field theories to compute some energy levels of atoms in a harmonic trap, and they were getting like real good, realistic results. However, they wrote some very famous papers. You'll find that there are a bunch of mysteries that appear when you actually study this. There's a whole bunch of mysterious sleights of hand or things that look like statements in usual CFT, but when you dig into them, they don't really make sense. Then I'll point all those out, but if you see any along the way, please feel free to shout them out. I'll review a little bit of relativistic conformal field theory. And then finally, I will introduce this object I call the harmonic trap geometry. And I'll explain how the harmonic trap geometry resolves all of the problems in this previous analysis. And so my goal for today is, roughly speaking, to prove to you to argue to you that not only are non-relativistic CFTs, showing up in all sorts of places in physics, I want to convince you that they are quite successful, but that they weren't really on a solid foundational footing. And I want to argue to you by the end of the talk that a whole bunch of things, that they behave just like usual relativistic CFTs, but with some fun twists. So it's not just straightforward. You don't just take all your favorite formulas from relativistic CFT, plop in z equals 2, and then declare yourself victory. Okay. So I guess.
Sorry, can I ask? Can you comment on this thing that happens in nuclear physics, where sometimes you think you have scale invariance, but then you actually have discrete scale invariance when you quantize, like when you ask the wave function to be regular, and so it breaks the symmetry. This happens a lot in nuclear physics. It's Efimov states and things like that.
Yes. Right. Those are the ones that are like related to conformal quantum mechanics, right? Because it's breaking.
It breaks scale invariance and then becomes discrete.
So I do have things to say about that, and there are some tantalizing relations to conformal quantum mechanics, but we would have to talk about it after, because we're not going to. Yeah, it's not going to come up.
Yeah, it's just like when you write the Lagrangian, you feel like you have conformal symmetry or scale invariance, and
yes,
but actually you don't. I'm wondering which of these cases can fall in that category.
Yeah. So I have a bad answer to that. Is if you took the system that I'm studying here and you said there were no spatial directions, then it basically should reduce to conformal quantum mechanics. And to be interesting, you would have to then break scale symmetry. Yeah, but that's Yeah, I mean, so all of the examples, I guess if we said, I mean, that's just an example of how I can recover what you're talking about from this formalism, but it's not really a sharp answer because I know that the nuclear physics people are not working in one dimension. So yeah, I don't have any sharper comments. Sorry. Okay, so yeah, let's talk a little bit about these things called fermions at unitary. So what's the idea behind these fermions at unitary? Also called BEC, BCS crossover. So the idea is quite simple and it's very general. So we can take an n particle Hamiltonian. Okay, very general n particle Hamiltonian. So I'm going to write it out. Sorry to belabor the point. So general n particle Hamiltonian, A equals 1 to n minus h bar squared over 2m nabla of A squared plus sum L equals 1 to A minus 1 V XA minus XL. Okay, so here we go. Here's a very general Hamiltonian with very general interaction. If I was being like very cheeky, I might call this quote unquote a very general gas of electrons or gas of particles. And I want to really study systems with two approximations made. The first approximation I want to make is that whatever gas I'm studying is a dilute gas. So by a dilute gas, I mean that effectively we're never going to have a situation where 3 particles are going to all come in and scatter at once, or 4 particles or 5 particles. When it's dilute, everything's basically dominated by the 2 body interactions. So that's assumption 1. And assumption 2 that I want to make is that the systems I'm studying, I'm going to basically consider scattering experiments, but I'm going to consider them at low temperatures or low energies. So let's quickly talk about 2-body interactions, right? So imagine I have 2-body interactions. I'm studying some non-relativistic scattering problem. The 2 particles are coming into each other, and all I have to worry about is 2 particles scattering. I can work in a convenient set of coordinates. A convenient set of coordinates is to work in some center of mass frame. So I change my wave function into center of mass coordinates and a relative wave function. Then in this case, basically all of the physical information is in how this relative wave function changes before and after scattering. Right, so what people will normally do is they'll take the 2-particle wave function, psi x1, x2, right? It is equal to psi center of mass, r, psi relative wave function, little r. Then you take this psi relative wave function, little r, and you do some sort of partial wave expansion. I'm not going to get it right. There's like a whole bunch of coefficients here, maybe some pn's. I forget what goes in here. I guess it must be r. So you're going to do some sort of partial wave expansion, and then all of the information about the scattering is in the distortion of this relative wave function. So now I also want to make the assumption, like I said, that I'm working at low temperatures or energies. So in this limit, the things I'm scattering in are at some very long wavelength. And if I come in and I'm imagining I have some sort of potential well, if I'm working at really low energies relative to that potential well shape, then I'm basically scattering off of a speck, right? The shape of the well and details of the well don't really matter. And so that basically means that the dominant interactions are going to be the S-wave interactions. If I wanted to make this quite literal, if I wanted to literally think of systems that only have S-wave interactions, then I would just replace my potential by a delta function potential. So now basically all of the information, so that basically just says that this creature here just truncates at 0th order, 0, 0. And then all of the information about the scattering problem is basically just encoded in the S-wave scattering, in how much the wave function distorts, the S-wave wave function distorts as the 2 particles scatter past each other. Okay, so all of this can be encoded in some phase shift of the wave function. But this is usually called the scattering length, A, this free parameter. Okay. And the systems that we are most interested in, so this is not really an approximation, but this is just the limit we're interested in, is we're interested in the limit where the scattering length goes to infinity.
Is the phase shift or?
It is the scattering length is basically the phase shift, yeah, that's right. So the idea is we're interested in sort of, yeah, that's right. We're interested in this when scattering length A goes to infinity. Yeah, because again, so let me just summarize. I was studying a very dilute gas of particles. I'm studying it at low energies and low wavelengths. The particles scatter in, and the most difficult systems to treat are the ones where even though like they're basically almost pure contact interactions, when they do go and hit each other, like they have some really dramatic distortion of the relative wave function. This actually describes many physical systems extremely well. Like I have a whole list of different systems where this applies, especially various ultra-cooled gases of atoms. It's yeah, it works surprisingly well. So this limit here, when A goes to infinity, this is what people call the unitarity limit. It's an unfortunate name because it doesn't mean all these other systems are non-unitary. It just means that this limit is also when the S-wave interactions saturate the unitarity bonds. The S-matrix unitarity bonds. I know this is a lot, but it's just some old school non-relativistic scattering. I can, yes.
In fact, there are fermions. How does it affect Stony because of fusion principle?
Yeah, so all of these assumptions still hold. It really just changes, it changes the details of, it changes the details of the calculations when you're computing like the relative wave function or something like that. Or I'm going to write down a Lagrangian, and it changes what the field theoretic description is. Yeah.
Do you have bosons unitarity?
Yeah.
Oh, you do.
Yeah. So you can right. So let me write down a Lagrangian, and I think then maybe this will come back to both of your points. So field theoretically, I can write down a Lagrangian for these systems. So here's an example of one. This is the fermions at unitarity. So stick with me here while I write it out. Minus 1/2 nabla psi squared minus c naught over 2 psi up dagger psi down dagger psi down psi up. So this is sort of the field theoretic version of the thing I just described, right? This is the second quantized version where I was studying fermionic things. It's this is just free fermions, makes sense. And then because I said I'm basically trying to study delta function interactions or things that are S-wave dominated, I added this psi4 term. Right? Phi4 interactions are the relativistic version of a delta function. And indeed, this problem of tuning to the unitarity limit or tuning A goes to infinity, right, where these distortions are very big, is just the same thing. Whereas if we took this creature here, we computed the beta function, and we tuned it to be 0. It's like tuning to conformality.
So this is marginal in whatever governing dimension?
That's a good question. No, it's not.
So how are you doing the beta function?
This is so what I'm saying here. Yeah, this is like if I was talking about the analog of some Wilson Fisher thing. Yeah, I was being intentionally a little quiet about that, but yeah. So if I was in two dimensions, this term here is obviously boring. If I was in 4 dimensions, I can do some Hubbard-Stratanovich transformation and then study that system instead. And then in 3 spatial dimensions, then this is like an interesting problem. Yeah, that was the next point. But I wanted to come back to the question about the fermions and also your question about bosons at unitarity. Indeed, so this Lagrangian here is a Lagrangian people talk about when they talk about fermions at unitarity. If I could easily just replace all these psi daggers with phi's. That's called bosons at unitarity. And actually, more generally, we're non-relativistic systems. There's no spin statistics. There was no reason for me to have these fermions have little size or whatever. I can put in whatever I want. People study anyons at unitarity. Those are actually the most interesting ones. David Tong has many papers on that. Sun has many papers on that. The bosons at unitarity are unstable fixed points usually. So they're not always good, but they're just easier.
Can I add master? What can you add if you can't add the fermions?
Hmm?
What can you add if you can't add? What is the relevant information that makes it unstable? You don't have here. It's not important.
I should know.
Yes, that's fine.
Okay. Okay, yeah, so. Okay, yeah, so I guess, yeah, I just wanted to quote, normally I would go through this in more detail and I would go through all these diagrams and whatnot. But I just wanted to, maybe I'll just quote these things. I guess Adar basically already presaged all of these points. So there are QM arguments, QFT arguments, and if this matters to you, experimental validation. So I'll just write experiments that tell us the following things. In D equals 2 dimensions, this system here.
Is that space then or space?
Good question. Yeah, so I'll always work in D plus 1 dimensions, so D is space. In D equals 2 dimensions, this is a free Fermi gas, this system. in D equals 4 dimensions, this is a 3 dimer. Is it dimer or dimer? Dimer, let's say gas. So this is exactly what I was saying. What you do is Hubbard-Stoyanovich trick, and then the Hubbard-Stoyanovich field is like these fermions basically clump up together into some bosons, and they basically behave like free particles. And in D equals 3, this unitarity limit, the fixed point or unitarity limit, is strongly interacting. So yeah, there are many arguments for this. There's really nice arguments of quantum mechanics arguments by Nusanov's father-son team at Washington University in St. Louis. And so the point of all of what I'm trying, and this is obviously the one that's relevant to real life, this D equals 3 problem, right? Because it's 3 plus 1. And this is the one that describes this BCS-BC crossover. And yeah, so it's intrinsically some strongly interacting problem. Why am I telling you all this? Well, I'm telling you all this because I just wanted to convince you that all the games you can play with usual CFT, you can play with these non-relativistic CFTs. So what's one game you could play? Like if you wanted to set a strongly interacting fixed point, what kind of game could we play? We could play the same game we play with something like Wilson Fisher or something like, or Ising, right? We can work in D equals 4 minus epsilon dimensions, or D equals 2 plus epsilon dimensions. And then we can compute anomalous dimensions. We can compute anomalous dimensions of various objects. And so if we wanted to compute the anomalous dimensions of something in this D equals 3 system, this strongly interacting system, which describes the fermions at unitarity, or this BEC-BCS crossover, we can work in D equals 2 or D equals 4, do some epsilon expansions, do Feynman diagrams, play all the same usual games we play in usual quantum field theory. There's nothing different. In another world, I would have loved to have talked about how exactly you go through with all that, but there's simply no time. Now, for those who are keen enough to sit right in the front of the talk, I'll just show you how well this works, and then you'll just have to nod and assert it to everyone else. So here's how you can see there's experimental results, and there's the 4 minus epsilon and the 2 plus epsilon. And I'm not even going to let you look at the legend. You can already see the lines. Look how squished together they are. That means like it worked, right? So it worked. It's beautiful. And everyone behind you just going to have to trust me. It works really, really well. Like that's some one loop calculation, and it just matches some experiments called atoms in a harmonic trap. It matches it amazingly.
But what works? The epsilon expansion?
Yeah, you do this epsilon expansion and you compare it to experimental results for these atoms trapped in a harmonic potential, and it just works.
If D equals 3, you say at first order you get a very good description of it.
Yeah, that's right. Yeah, already. Yeah, that's right. Just using first order perturbation theory, you match these real systems.
It usually requires some accident. That's not even true for the O2 or O3 model. No, it's not. It needs to be explained.
And
For example, the fact that it works in the Ising models for some operators related to some accident, blah blah. Is there some accident here?
I have no clue.
Okay.
Yeah, and actually, to your point, to even double down on that point, I mean, recently we've seen these papers saying like, yeah, like these papers of Slava and others talking about, oh, like, you know, does the 2 plus epsilon expansion match 4 minus epsilon, or is it just a subsector of the other theory or something like that? And I have no clue whether or not that's true here as well. It could be that they're both approximating. Yeah, they're both. Yeah.
That's usually an issue with like heavy operators and things.
I mean, this. Sure. I mean, I just meant to say that this is the exact analogous problem. This is true. Yeah, for these systems. So
it seems to be like asking for a fuzzy sphere, no?
I mean, maybe.
Well,
yeah.
Here.
That's very 2026 of you to say that. So yeah, so I said you can compute anomalous dimensions, but I guess the question is of what, right? So that's question 1, and 2 is why? Why would I like? Okay, you can compute anomalous dimensions, but why are we going to do this? We don't just do it for fun. We do it usually because it matches something. I asserted earlier that it matched some experiment, so we should know what and why. So what are we going to compute? So now we get to the formal fun stuff. Right? This was all experiments, boring. Now we get to do formal nonsense. So, of what? So, local primary operators, of course. So the definition of a local primary operator in a non-relativistic CFT is pretty straightforward. D acting on such a thing, so a local primary operator, curly O, if D acts on it, it's proportional to, it has a well-defined scaling dimension. If M acts on it, It has well-defined mass. And these operators, when inserted at the origin, they are killed by the analogs of the special conformal transformations. Let me come back to a point I should have made a long time ago. These KIs are boosts. They are not special conformal transformations. However, algebraically, in the Schrodinger algebra, they play the role of special conformal transformations. So indeed, this is algebraically, this is the correct notion of a primary operator. Okay? Well-defined dilatations, well-defined mass, and annihilated by some version of special conformal transformations. And just like the usual CFT, there's a notion of descendant. And descendants basically are just taking one of these operators and hitting it with some number of derivatives, d0, di, etc. Okay, so these are descendants, and you can clearly see just as an artifact of this algebra here, if I hit it with spatial derivatives, pi, that shifts the conformal dimension delta to delta plus 1. And if I hit it with time derivative, that just shifts it to delta plus 2. Sorry that it's all the way down here, and I know that's hard to see, but it just follows from that. It's just straightforward algebra. So that's just the z equals 2 scaling hanging around. So those are local primary operators. Now let me give you some examples in something like the free theory, or a theory described from perturbation theory from a free fixed point.
So all of these descendants have the same n, right? Or
Yes, that's right, because m commutes with everything. That's right. So let me just show you some examples. So you see, I'm giving the talk not in the logical order, I'm giving it in the historical order. And the reason is because the historical order has a whole bunch of issues, which I would hope to resolve. So, and people are usually focused on theories that have Lagrangian descriptions. And the whole point of what I'm trying to do is trying to leave the realm of Lagrangian descriptions for these non-relativistic CFTs. So what are some examples of primary operators? Well, if I had something, and please excuse me, I know I wrote down the non-relativistic CFT, I wrote it down for fermions. I'm going to switch to bosons here so I don't have to write down all these indices. So what's an example, right? Phi dagger is a perfectly good primary operator. Phi dagger, that's some composite operator. It's well defined, we're in the free theory. That's a very good primary operator. dt of phi dagger is obviously not, right? Because it's a descendant of the other one, but something like phi dagger dt phi minus dt phi dagger phi, that's a good primary, right? This is like these are just some composite primaries. And you can play all the same games. Again, if I had some Lagrangian description, this could either be my bosons at unitary, or it could be literally the free theory. I can compute anomalous dimensions in perturbation theory by just taking 2-point functions of these operators, writing it down, computing the 2-point function at, that thing I called C naught star, where the beta function was 0. So you can play all the same diagrammatic games. So those are primary operators. And I also note, since I'm just writing things down in free field theory, I note that like all of our favorite generators, like those creatures on that board there, can be written in terms of the fields. I'm not going to write them all out, but let me just show you 2 of my favorites. So one of them is this mass. So the mass, for example, can be written like this in the free field theory. So this makes a lot of sense. This phi dagger phi is the number density, measures how many particles there are. And then obviously you just weight it by the mass, and that tells you the total mass of some state or some operator, right? Counts how many things are in it, weights it by the mass. That's the mass charge operator in terms of the free fields. And also, I'll show you another favorite of mine, is the C naught. That's the special conformal transformation. Here it is written in terms of the generators, or in terms of the fundamental fields. It looks like x squared over 2, phi dagger phi.
What is lowercase m in the definition of capital M? Why do you need that number?
That's the mass charge of my fundamental field.
Oh.
Okay.
you have your primaries are labeled by delta and little m, right?
Yeah.
Little m is not like unique, like
That's right.
Little m is like quote unquote dimensionless, right?
yes, but it's not one for the whole theory. Like different operators have different little m.
That's right. So
It's not like central charging to the.
yeah, agreed. Yeah. So
Is it a problem that you have infinitely many operators with the same m?
what are the infinite many?
All descendants have the same little m.
Sorry. No, I mean, because they're all going to arrange into some conformal multiplet, so it's not.
Like a charge scalars.
Yeah, exactly. Yeah, I mean, one way that you can think about M is you can just pretend it's like some U1 charge symmetry or something.
Is it actually U1 or?
No, it's probably R, or I have no idea what the quantization condition would be. Yeah.
So can I ask a random question?
Yeah.
Is there OPE this or not?
Yes, there is an OPE. I haven't told you what it is, but I don't think we've needed it thus far, right?
I mean, if you want to do bootstrap, you want to know.
Oh, yeah, that's so far, that's so, that.
So because you said you want to leave the Lagrangian realm, so.
Absolutely, and so indeed, part of the title of the paper includes the words "and the path to the bootstrap," because we're trying to understand basically all the basic things that we would need to. Yeah, so it turns out there is an OPE and it does converge. But yeah, getting there is hard because results that have existed in the literature to date are not actually powerful enough to get you to that statement. There are claims that it is, but they're just false.
So it's confusing there is an OPE because like it's a non-relativistic limit, so crossing do not hold non-relativistically. So the fact that there is an OPE, different channel.
Why would crossing not hold?
Well, crossing is a relativistic concept.
What?
For the S matrix, not for.
Not for correlators too. I mean.
Why?
What?
Okay.
I'm wrong.
No,
I mean, if there is, it's amazing. Yeah. Anyway, so.
I mean, I think if you have a path in the goal, yeah, okay, we can talk about it. Okay. So that answers the question of what we are computing scaling dimensions. And then the question is, I didn't answer still, why? So I'm going to make an assertion. No, I will justify it. So why do we care about scaling dimensions, right? So question, why scaling dimensions? Like, what does this match in some experiment, right? Why compute these scaling dimensions? And the answer is that scaling dimensions of these operators give the energy spectrum. Sorry, my writing is devolving as the talk progresses. Energy spectrum in this thing that I call the harmonic trap. Well, not I, everyone called it that before me. In this thing called the harmonic trap. So that means if you take this as your Hamiltonian, you take HHT is equal to P naught plus omega squared C naught. Okay, this is called the harmonic trap Hamiltonian. And it's actually kind of a sensible idea. So the idea is that you had your thing that you would naturally want to call the Hamiltonian, P naught, and you've added this term plus omega squared C naught to it. Why is it called the harmonic trap? Well, I didn't write this out randomly. If you take a look at what C naught looks like when written in the free field theory, it looks like the number density, but weighted by this quadratic term, right? So the way you can think about this is, you're putting the theory in a harmonic trap, or another way of thinking about this is like, this is sort of the non-relativistic analog of putting the theory on a cylinder. Right? You're gapping the spectrum, it sort of makes sense because before I had this dilute gas of particles and they can just run away, the spectrum can be anything. But when I put them in the harmonic trap, they sort of get confined and it discretizes the energy spectrum.
What is omega? So
Omega is just some parameter. Yeah, I should have mentioned that. You can set it equal to 1, but it's conventional to leave it in.
Like the radius of the.
It's like the radius of the sphere. Yeah. So it's conventional to leave it in. And so there is this statement that exists in the literature from Nishida and Son. So, all right, Nishida, Son, okay, and it goes by the name in the literature, state operator correspondence. Okay, and this statement says the following. So I'm going to write out the whole statement and then dissect it, and it's really important, so I'm going to write it out in detail. So let omega be the harmonic trap Hamiltonian, the HT vacuum. So it's the ground state or vacuum state of this Hamiltonian here. And let curly O a local primary operator made only of creation operators and with m greater than equal to 0, I guess I'll write little m greater than equal to 0, then this creates a state in the spectrum such that HT acting on that state is equal to omega delta O. Okay, so if you have the harmonic trap vacuum state, you attack it with this local primary operator made only of creation operators with a mass strictly greater than 0. And this corresponds to some state. That state is an eigenstate of the Hamiltonian, and that eigenvalue is proportional to the scaling dimension. So this is the experiment that people were studying before, right? They were taking, you had this gas of atoms, right? You put it in a harmonic trap, you confine it to a harmonic trap, you took a look at the energy levels, and what they would do is they take the corresponding Lagrangian, they compute anomalous dimensions of that thing, and then they would just basically match it to the spectral lines that they measure. So this is the thing that's called state operator correspondence. So what's the problem with it? So the problem with it is the state operator correspondence is supposed to work for things that are not just primaries, it should work for descendants, but it truly only works for primaries, as presented in the literature. Secondly, I said it should only be made out of creation operators. What is the definition of a creation operator if I'm not in free field theory or some non-relativistic limit? Another point is it says m strictly greater than 0. Okay, maybe we could do a little better. Maybe we could do m greater than equal to 0.
Omega is supposed to be annihilated by everything, including M. Or
Yeah, that's right. And that's right. This is like the conformally invariant vacuum. So yeah, those are a whole bunch of issues. Like I don't know why it should only work for primaries. Maybe it does. That's just unfortunate. Or m greater than 0. But this at least begs the question, or raises the question. Sorry, what do I mean by made only of creation operators? Okay, so those are some of the mysteries. So let me just turn to this. So yeah, let me do a quick little recap here. Now I only have red chalk. So what happened to the white chalk? Hides behind this little ledge here. So let me recap. So Schrodinger CFTs, they exist. They're conformal enhancements of non-relativistic systems. So Schrodinger systems exist, and they're like CFTs that are non-relativistic. Two, they appear in all sorts of different systems. Basically, any Hamiltonian with two-body interactions at low energies, that's going to be described by some Schrodinger CFT. They also show up in holography, null reductions, blah, blah, blah. And they have some notion of local operators, primaries, descendants, scaling dimensions. And for some reason, these things give scaling dimensions, give energy levels in a harmonic trap. Okay, now let me talk about all the mysteries that we had. So, oh no, that was my amazing state operator correspondence, and now it's gone. Oh well. So what were some of the mysterious points? So number one, there were primary descendants. They were lurking the entire time. Nobody pointed them out in screen below. So if we go and we come over to this board over here, we take a look at the commutation relations. Oh, it was this box. We can clearly see that Ki and Pj, if the mass of something is 0, then they commute. So what this means is that if I have some primary operator O, and it has mass 0, and I attack it with a whole bunch of derivatives, it's still going to be annihilated by the Kj's. It's still going to be 0, and C naught is going to be unaffected as well. So this leads to primary descendants. And what did people do in the literature? So, and let me just point out, this doesn't have to be some fundamental field. There's a really good primary operator. It's one of the most important ones, this number density. Right? So there's a good example of a primary operator that has mass 0. The number density and the free field theory. And what did people do? They had a really brilliant solution when they encountered this problem. They gave up. And they would just say, let's just assume m is not equal to 0 in every single thing that we talked about. Next point is that state operator correspondence. So I mentioned in what sense is it actually a state operator correspondence? What does it mean to only be made of creation operators? What is a creation operator anyway? And I note that the same problem, literally every observable doesn't work. Right? Because by observable, I mean for something to be an observable, at least in this state, with this vacuum state, like the mass has got to be 0, right? Like to be an observable, it should be uncharged. If I'm going to add it to my Hamiltonian or something like that.
Why?
What?
Why is it only an observable? It's uncharged.
And I'm using a restrictive notion of observable. I'm just talking about things that I can add to the Hamiltonian to deform it that aren't going to explicitly break my like Galilean symmetry or something, my Schrodinger symmetry.
No, but that's not the definition.
Or not my Schrodinger symmetry. Sorry, my mass. Yeah, I want to preserve my symmetry. I want to preserve my mass. Okay. Yeah. So, for example, the number density, which is something really obvious that you could turn on to deform the theory, is not something that has a state operator correspondence. And this would be like turning on some chemical potential, for example. The third one, I didn't actually talk about it in detail, but it's kind of a fun point, is that these non-relativistic theories have a whole bunch of non-renormalization theorems. How are we doing on time? Doing okay. So they have a whole bunch of non-renormalization theorems. So let me explain this very fast. So if you have Lagrangian theories, you have some sort of splitting into creation operators and annihilation operators, usually. And since the mass is just equal proportional to the number density, particle number, mass is conserved, mass, so therefore particle number is conserved. Okay, so in Feynman diagrams, this basically means virtual particles can't appear in loops. And so what it means when you actually write it out is that if you had, so I'm using some notation here where let's say creation operators means I have a propagator, like they have a propagator and let's say it runs with an arrow to the right and annihilation operators runs to the left. It means that loop diagrams made out of creation operators are non-zero. Loop diagrams made of annihilation operators are non-zero, but loop diagrams that have a creation operator and an annihilation operator in them are zero. Okay, and what this means in practice is that if I had some composite operator, let's say phi dagger squared, maybe I shouldn't write it like that, I'll write phi dagger, and I wanted to compute in perturbation theory, it's anomalous dimensions, that's perfectly easy, right? I'm going to have the operator, it looks like this, and then I could have maybe this loop diagram, and this loop diagram, and this loop diagram, and so on and so forth. And likewise for the annihilation operators, but something, again, like that pesky number density, which is an extremely important observable, it basically is not renormalized at all, because you will see that there is going to be no way that I can actually close this into some unclosed loops. In a CFT language, what I would say is that the OPE, if it exists, to the question asked earlier, the point the question asked earlier, is completely regular between creation and annihilation operators. This is some perturbative diagrammatic proof, and it's curious to ask if it holds non-perturbatively. And let's see, how are we doing on time? Shockingly well, actually. So we can basically, my point is we have all these mysteries, and the question is, can we actually address them in some systematic way?
Phrase a non-normalization theorem without perturbation theory. You're saying that the normal dimension of some composite is the sum of normal dimension.
Yes, that's right. So I can phrase what I wanted to say non-perturbatively. So pretend I had some composite operator. Again, that's even a tricky question if you're not in perturbation theory. What do I mean by composite operator? But I want to say something like, pretend I had an operator that's called phi dagger cubed phi to the 7. Okay, my claim is that its scaling dimension is equal to the scaling dimension of phi dagger cubed plus the scaling dimension of phi to the 7. Now again, what I mean by composite operator is even a little bit of a weird concept in a general theory, but actually that, as we could see, this will, like, even the definition of these composite operators comes somewhat canonically from the discussion. Well, yeah, then the following discussion. So, okay. So in order to resolve every single mystery in the last 5 minutes, we just have to review one other piece of quantum field theory. So let's talk a little bit about usual relativistic CFTs. So recall that in usual relativistic CFT, it's all pictures from here out. I promise everything in the paper is rigorous, but we can do everything from here just with pictures. So in usual relativistic CFT, recall that what we're interested in is we're interested in Lorentzian CFTs that are unitary, aka they're reflection positive when Wick rotated. Now, so they live on, let's say, R1, comma D. Okay. Now recall that R1, comma D is not invariant under conformal transformations. Let's just go quickly. Let's even go to Euclidean CFT. Euclidean CFTs do not live on RD, right? They actually live on SD, and it's super important that you have this point at infinity for the space-time actually be closed under the conformal group. Likewise, Lorentzian CFTs don't really live on R1, comma D. You can take R1, comma D, you take its closure, you get some sort of S1 times SD quotient Z2. And then this space has closed time-like curves, so you decompactify it, and you get some space, and twiddle is equal to R times SD. This is the Lorentzian cylinder. Okay, and then, as people probably know, you can draw a picture of the Lorentzian cylinder, and it looks like this. And your usual Minkowski space embeds as a Poincare patch in this Lorentzian cylinder. Okay, so here's Scri, here's plus, minus, and not. So usual Minkowski space embeds as a patch in this cylinder. And this is the thing which is actually closed under the conformal group. Okay, now time translation on this Lorentzian cylinder, let's call that tau. Time translations on the cylinder are generated by some Hamiltonian, I guess, the thing that generates it. And when you pull that back to Minkowski space, when you pull it back to the plane, that generator is, don't all shut it out. Okay, I was a trap. I was hoping somebody would shut out D. It's not D. It's the Lucier-Mack Hamiltonian. When you pull it back to the plane, this is P naught plus K naught. This is the Lucier-Mack conformal Hamiltonian. This is the thing which generates time translations in this cylinder. You might ask, where is D? Where is this thing? We always say, oh, it's usually time translations I thought on the cylinder were generated by D. That's not true. When you Wick rotate the Lorentzian cylinder to the Euclidean cylinder, then the Hamiltonian for the Wick rotated time is dilatations when pulled back to the plane. Okay, so if I was going to say differently, yeah, okay, so D tau Euclidean looks like D. Okay. So this is, and the Euclidean picture is where you get things like a state operator correspondence and things like that. So there's a whole bunch of ingredients involved. Now let's see what happens to this picture when I plug in that I'm working in D equals 0, right? So that's, or one plus 0 dimensions. So when I'm just studying like ADS2 CFT1 or something like that. Well, it's pretty straightforward. Actually, all of the things still hold. You just change all these D's to zeros. And the analog of the Lorentzian cylinder is actually 2 copies of R. So I guess I can draw a picture of it really easily. It basically says that there is some nice map you can do that takes a line to 2 copies of the line, right? If this is the origin, if I was now in the Euclidean version, if this is the origin in Euclidean space, then I have some sort of radial slices that go outwards like this. This point here at 0 becomes t equals minus infinity down here. And there are lines that radiate upwards and lines that radiate downwards. And this is really emphasized in works of Ashok Sen on 1D CFT. Why am I telling you all this? Well, I'm telling you all this because one nice thing, or one thing that happens in the CFT1 case, is that there actually is no state operator correspondence in CFT1, or at least it's not the usual state operator correspondence. The usual state operator correspondence says local operators are in one-to-one correspondence with states in the Hilbert space. But in 1D, you can clearly see that that's not the case. Instead, you can see when I cut my analog of the cylinder that I'm going to cut 2 copies of R. I'm going to cut 2 disconnected copies of R with a different orientation of time. So what that actually means is that local operators are in one-to-one correspondence with states, but not in the Hilbert space H, but with states in the thermal field double Hilbert space. 2 copies of H. And it's a conjugate because, again, one's been time reversed. So to say it again one more time differently, local operators are in one-to-one correspondence with states in a thermal field double. So what does all of this have to do? Why did I review this relativistic CFT? And why did I review specifically 1D? Well, it's because I wanted to basically say, so let me say, I'm going to introduce and end with the analog of that in non-relativistic CFT. So again, we only need pictures. So in Schrodinger CFTs, whatever they are, there are some correlation functions. And those correlation functions should be related to one another on Schrodinger-Weil equivalent geometries. You can make this notion precise using the formalism of Newton-Cartan geometry, but here today we can just think about it in terms of pictures. Let me give you a little bit of let me give some intuition for what's going on. So what are Schrodinger-Weil equivalent geometries? That's some notion of Weil equivalent geometry, but instead of for the conformal group, for the Schrodinger group. Let's look at our Schrodinger group. As was mentioned right at the start of the talk by one of the participants, there is really only conformal symmetry in time, and the space-like directions are just sort of there along for the ride. They get squashed along for the ride based on this Lifshitz scaling properties. So roughly speaking, and again, you can make this precise using this Newton-Cartan geometry, the space of Schrodinger Weil equivalent geometries to any geometry you have is roughly speaking, you just see what's going on with your time direction. Take a look at Weil equivalent geometries there, and then see how the space-like directions get squashed along for the ride. And so what this means is at an intuitive level that can be made precise with formulas, if I'm studying a non-relativistic theory on R1 plus D, okay, I basically just treat it as if it has D space-like spectator directions. And so the analog of the cylinder geometry is something I call M harmonic trap. And this is equal to R times S naught times RD. Right? And you can see exactly where this 1D CFT picture came before. I basically have a 1D CFT in time with D spatial directions along for the ride. I said, what happened to if I had one time-like direction in CFT1 before? It gets split into R times S naught. That's the analog of the cylinder for it. And these spatial directions come along for the ride. You can make it very precise. You can see that there's some analog of like Poincare patch and everything like that. But for the sake of time, I'll just show you the punchline. So the punchline is I can basically draw a picture exactly analogous to the picture I drew on the other board there, where I say, okay, I had my original CFT living on R1 plus D, and there's some sort of equivalent picture where I break it up into two sheets like this, and local operators here, inserted at the origin here, O, correspond to a state in a thermal field double focus space. Right? You can see what's happening in radial quantization. I have some sort of ellipsoid shapes that wrap around a local operator. They're ellipsoids instead of circles because I have this modified dispersion relation in the non-relativistic CFT. And one upper half of those ellipsoids are coming here onto this plane. And the bottom half of the ellipsoids are coming here onto this plane. So in the non-relativistic CFTs, you again have a local state operator correspondence, but local operators are in one-to-one correspondence with states in a thermal field double. Okay, so for the last 2 minutes, oh, yes, I should also tell you one other thing about this. I should say, why is it called harmonic trap geometry? Well, it's called harmonic trap geometry because if you go and you check what generates, well, this is the Euclidean picture, but if I did the Lorentzian picture, and I checked what generates time translations in the space-time, it's exactly P naught plus omega squared C naught. So you can see that the analog of the Lusher-Mack Hamiltonian for these in this space-time is exactly this harmonic trap Hamiltonian. Okay, so what are the consequences of this? So I told you all this, I said there's some geometric picture. Well, it basically resolves all of the previous issues. So it tells you there exists a state operator correspondence, right? It's one-to-one correspondence with states in this thermal field double picture. It's very nice, right? It also defines for you what a creation operator is. So for example, a creation operator can be just defined as something which is dual to a state, which looks like the vacuum on one side, and just fires a non-trivial state of the other side. Likewise, a creation operator, or an annihilation operator, is just the opposite. It fires a non-trivial state up one side and not up the other. And opposite operators like the number density, right? This was phi dagger phi. He just looks like a state, which looks like phi going up both sides. So it gives a nice picture of what, like some full version of a state operator correspondence. So this basically means it works now. I drop this mass greater than 0 restriction. It also means that I have defined for you what a primary is. And the other one was, oh yes, it only worked for primaries before. I can show that, when you wick rotate the Hamiltonian here, that it turns into dilatations. So it works for things that aren't just primaries, it works for their descendants as well.
So can you explain why it works for the descendants now from this point of view? So before they just had half of it, so they only saw an annihilation operator, that's fine. Why would
No, that's not why it only worked for them before. You see, what happened also in the literature before was that they took this Hamiltonian P naught plus C naught, and they took a look at its fixed points, right? Because that's where in and out state should be defined. And they saw the fixed points of this thing are like -1, +1, 0, +1, 0. And then they said to themselves, okay, well, what we'll do is we'll take a local operator at the origin and we'll just move it by translation to the point -1 to prepare an in state, or we'll move it like literally with a translation to +1 to prepare an out state. This is and then what they found was is this conjugation basically turned this harmonic trapped Hamiltonian, when you conjugate it by P0 on both sides, it turns it into C0 minus I omega D. So this was the condition. This is why they said it only worked for primaries, because only if you had a primary state was this term going to drop off and give you just this. This was the wrong thing to do. You weren't supposed to bring a point at 0 to -1 or a point at 0 to +1, right? The right thing to do is take the point at 0, bring it to -1, while simultaneously bringing the point at infinity to +1. So they just did the wrong conjugation. This geometry, though, just makes it immediately clear. So that's resolution 1. I basically just said there's a full state operator correspondence. It works for everything. And
Infinity is also a fixed point, right? Is infinity also a fixed point?
Let me rephrase. So if I was doing dilatation, so if I wanted to take a look at the dilatation operator, it has fixed points at 0 infinity, and I want to map its fixed points to these fixed points. And they just did that wrong. And okay, and this picture also makes it clear why non-normalization theorems work. Why should why should operators, dual to states in the daggered and undaggered sectors, why should they have regular OPE? Well, it's obvious. They live on completely disconnected spacetimes. Okay. And then finally, I didn't actually set up the framework to talk about this. In the paper, we also classify all projective, unitary, irreducible representations of the Schrodinger algebra, such that they also have positive energy condition for the harmonic trapped Hamiltonian. So we can basically we wrote down all the analogs of every single unitarity bound for these systems. And we even find there's some analogs of that these number density operators, these composite operators play some role analogous to like double twist operators and things like that in usual CFT. So that's the punchline. So let me just summarize one more time. Schrodinger CFTs exist, and they had some putative attempts at some state operator correspondence, and that was already good enough to match experiments really well. Like I note again, they basically got the right answer by doing this just for primaries only. But this picture here basically explains that, okay, you can play all the games that happen for usual CFTs with these non-relativistic CFTs. And as soon as you have this clear geometric picture, all sorts of mysterious, let's say diagrammatic proofs of non-renormalization theorems and like nice OPEs and attempts at state operator correspondences immediately just become obvious because, they basically just become this picture. And again, you can prove all of this algebraically. We do it in the paper. We use these pictures, but then we show that the math corresponding to it gives like proper analytic results. So with that, I guess I'll just end here. Yeah.
A very nice question there. Isn't this Schrodinger CFT supposed to be some limit of a relativistic CFT where I take the speed of light to infinity?
So some of them can be, so yes, some of them can be thought of that way, but I wouldn't want to box myself into thinking of all of them that way.
But the algebra reduces, right? If I in a way that I can get the Galilean algebra from the Lorentzian algebra by taking speed of light to infinity.
So that's not, no. So if you just work at the level of kinematics like that, no. It turns into that other one I mentioned called Galilean conformal algebra.
Oh, I see.
Yeah, so this doesn't even have the right number of generators to be the Ininu-Wigner contraction of the algebras. However, when you take like as you mentioned before, when you take like something like your favorite massive Lagrangian and you split it into creation and annihilation modes, pull out like this e to the minus mt, like these plane wave factors and things like that, and then say, oh, m is much greater than, m is much less than, ct or whatever, then you recover some Lagrangian. It basically turns into one of these Schrodinger symmetric Lagrangians. But that's not really the same as just contracting the algebra. I know that was
something. If the properties, you could get some of the properties by taking its naive limit. Like just thinking about like OPEs, all these like story where you can just take some limit of the CFT properties and.
Yeah, I mean.
But you're saying it's really a disconnected. Sorry.
It's disconnected, but also not completely, right? Because so one thing you could do is you could take your favorite CFT and you could deform it by some Lorentz symmetry breaking relevant operator, and And those will flow to Lifshitz theories. And if there's some conformal enhancement, like if you pick your relevant operator correctly, it'll flow. So they are literally connected in the sense of RG flows. But yeah, kinematically, they're slightly disconnected, as you note. Yeah. There are questions, comments, concerns? Yes.
This is a, well, maybe very naive. This is a different limit than the limit that you take in CFT to get like Carolinian CFT.
Yes, but actually, funny enough, well, yes, most of the time, yes, that's right. Yeah, this would be the, first of all, the opposite limit, which because that's the ultra relativistic limit, and then again, as previously mentioned, even that turns into the other algebra. If you work in 1+1D, which is not an exciting place, then you could imagine you took a Carolian limit and then flipped space and time. I know this is like some sick, like disgusting thing to do. And you could say that was a Schrodinger symmetric CFT, but
right. So this doesn't teach you anything about like flat space holography.
Well, it kind of does. It's a bit of a stretch, but again, since one way to obtain these non-relativistic systems is to take your favorite Lorentzian CFT and do some null reduction. So physics, for example, if you take a null defect or something like that in a Lorentzian CFT and you do some sort of null reduction on it, you will get a defect in a Schrodinger symmetric system. In fact, your favorite things like light ray operators basically turn into things like these number densities, these m=0 things when you null reduce. So there are connections. In fact, that's kind of how we came to some of these problems. That was a lot, but since you're familiar with light ray operators, probably makes sense.
Is there something like a C function for these things?
That's a good question. So all of the ingredients of C functions exist in the sense of like people have gone and they've classified, this is the Weil tensor, this is the coefficients around blah, blah, blah. And there are, but nobody has shown that there exists a monotonic function, decreasing function on the space of theories. There are papers that claim that you can actually show that there are limit cycles in the space of theories, which might lead you to think that you can't have such a thing. However, I don't know if that analysis holds non-perturbatively. Because even this happens in relativistic CFTs. You could think there are limit cycles in some perturbative analyses, but non-perturbatively, it's not actually there. And so I just genuinely don't know the answer to that. There's also an analog of like central extending. So you could take this SL2R symmetry, you could imagine some Virasoro-like central extension, and you could ask yourself, is that related to these things? The answer is kind of. It's a little bit messy, but yeah. So I would love to know the answer. Yeah.
So in a setting where you want to study some higher dimensional relativistic theories, say by null reduction or by DLCQ, what does the 2-0 theory is the most exciting possibility?
Yeah.
What does this teach you?
Okay, well I guess that's a very broad question. I mean, it would tell me in the 2-0 theory, okay, here, let me make something up, which is true, but like a bit vague. In the 2-0 theory, there are interesting like surface operators, which are like null Wilson surfaces by integrating the 2 form. I guess I could do some null reduction. And well, first of all, I guess, I could do some sort of null reduction and I could say, oh, that's going to look like some line defect in this Schrodinger symmetric theory, depending on how I do the null reduction. But those are just words, right?
That's very ambitious. In the 2-0 theory, we've already been incredibly excited to calculate some energy levels in the harmonic trap.
I agree.
Beyond the ones that are dictated by supersymmetry.
I agree. So let me actually back up. Let me go to a simpler theory than that. Let's just take our favorite thing like so there's one tricky thing in these theories, which is whether or not there exists. So there exists obviously massless states and massless operators, right? Again, our favorite thing, the number density in the free theory was an example of a massless operator. But you could ask if there exists some version of a massless operator, which is like pure creation / annihilation operator, right? So creation annihilation sort of doesn't make sense when you have m=0, but you know what I mean? Like you could have like a field in the Lagrangian, quote unquote, or like a fundamental field or an operator which is not a composite, which has m=0. So it corresponds to a state in just one copy of the harmonic trap. Okay, when you do null reductions of those theories, if such things exist, it breaks or changes lots of the story. I sort of presented to you the easiest version of the story. Nobody knows any examples of such things, and they were thought to not exist, but they're consistent with unitarity maps. I promise I'm coming to the answer to your question. If you take, for example, the null reduction of non-abelian gauge or some gauge theory in 4D or free scalar in 4D, and I assume probably if I looked at the kinematics and scaling dimensions, some of the 2-0 theory in 6D, they probably have these m equals 0 states, and it really complicates lots of the story I've told today. So my answer to your question is I think that would be something very interesting, but it's going to be more complicated than just what I've presented here.
Which generator does M correspond to?
M?
In the null reduction? Or is it just the KK momentum or?
Yeah, that's right. So as you're familiar with when you do this DLC2, there's this whole problem of it looks exactly like the usual theory. It agrees with hidden perturbation theory. And then all of the complicated non-perturbative junk goes into the m equals 0 sector.
Yeah.
And so indeed, what I'm basically saying is when you study that, you'll get some sort of, in the null reduction, you get some Schrodinger symmetric theory. And it basically, this m equals 0 sector splits into two types of things. Things which are not dual to states in one copy of the harmonic trap, and things which are dual to states in the harmonic trap. And I'm saying things like non-abelian gauge theory in 4D, or sorry, just gauge theories in 4D, and probably the 2,0 theory because it's really fancy, leads to an interesting non-trivial sector here, and which we have some control over, but it's just, it again makes lots of the story more complicated. But in a way we have control over.
I mean, the m equals 0 sector is the one that we have principle really good control over. It's weakly coupled in 5 dimensions.
Oh.
So when you null reduce a 4D theory or
Yes.
to 3D, then typically the 0 mode sector is very strongly coupled and
Yes.
coupled. The nice thing about the 2-0 theory is that the m equals 0 sector is the weakly coupled sector.
Because you're greater than 4.
So
Okay, then
with that, so you might learn something.
I guess so. Yeah, okay, that sounds like a good thing to do. We went after 4D, I guess, by being silly. Maybe that was your question.
Yeah, no,
Wow.
small cookies.
Sorry, yes. Okay.
Right. Maybe we should just collapse and have.